At the end of this lecture, you should be able to tell me the rank of a tensor, which is just a list of numbers or a vector. In the last demo, we used constants to build up our computation graph. In this demo, we'll use tensors. Tensors are n-dimensional matrices made up of primitive values such as integers, floats, booleans, strings, etc. A tensor is a central unit of data within a TensorFlow program. It flows through the nodes which act on it and produce new tensors. Tensors are the edges in our TensorFlow computation graphs. The code for this demo is in the Simple Math with Tensors IPython notebook. To start off any TensorFlow program, we'll import the TensorFlow libraries and alias it as TF. One thing to note here is that Data Lab comes with TensorFlow installed. There is no additional installation step that you need to perform before you use TensorFlow. We set up two constants, x and y, but the values for these constants are one-dimensional arrays or vectors. These are 1D tensors. The rank of a tensor is equal to the number of dimensions that it has. So this is a tensor of rank 1. Both these constants are tensors of rank 1. TensorFlow has math operations that can operate on the entire tensor in one go. For example, the reduce sum operation will sum up all the individual primitives within our tensor. Similarly, the reduce prod operation will find the product of all the primitives within the y tensor. Final div is the next computation that we specify. Notice that the input to final div is the output of sum x and prod y. We divide sum x by prod y. The reduce mean operation finds the average value of the primitive specified in the tensor. Here we find the average of sum x and prod y. Now that we've built our computation graph, let's instantiate a session so that we can run this graph. You can also instantiate a session using a simple variable in this way. This is not recommended though because it's very easy to forget to close the session, like I've done in this program. In TensorFlow, in order to find the value for any computation, you need to call session.run and pass in that computation node. Only then will you get the results. Let's say you were to execute print x or print y or print sum underscore x. That will give you the metadata details of the tensor or the computation that you perform. In the case of a tensor, it will give you its rank, perhaps its shape, its data type, and so on. It won't give you the value of the tensor. To get the value of a tensor, you have to compute it using session.run. This is true even if the tensors are just constants. Run these lines of code and you'll see the result printed onto screen. There are the value of the constants x and y, sum x, prod y. Notice that sum x sums up all the individual elements of x, prod y multiplies all the individual elements of y. We want to view this computation graph with tensors, so we write it out using tf.summary.filewriter, this time to a different directory, simple math with tensors. Run this bit of code. This will show you where tensor board has been launched and you can click on that to view your tensor board. And here under the graphs tab is the computation graph for this TensorFlow program. Notice that we added tensors and a few more operations such as reduce sum, reduce mean and so on. And the graph has already grown in complexity. If you notice in this graph, some of the nodes have been shaded in gray and have a plus sign within them. That's because that node represents a logical grouping of several computations, and you can set up this logical grouping using something called named scopes. We won't cover that right here, but you should know that it exists, and the computations within named scopes are grouped into one node. You can expand this node and see what the individual computations are. Another thing that might have struck you here is that you didn't explicitly compute the rank of any tensor. So how does this rank operation show up? The reduce mean operation, though, under the hood needs to find the rank of the individual matrices or tensors in order to compute the mean. That's where this rank comes from. The rank of a tensor, which is represented as a list, a single dimensional array, or a vector, is essentially 1. The number of dimensions is equal to the rank of a tensor.